Hello and welcome to this video where we will learn about distributed loads and how to deal with them in equilibrium or analyzing the equilibrium of beams and structures. So we see in this picture here, it's a picture of people celebrating the 50th anniversary of the Golden Gate Bridge. So many people, right? So the way that maybe if I'm a structural engineer or a bridge engineer and trying to check the safety of a bridge, what I can do is represent each one of these individuals as a single force. So they will have a lot of arrows going down. If you imagine like drawing a lot of arrows, and trying to figure out now the equilibrium that results from all of these arrows or forces together. Very inefficient process, right? So the way to deal with such loads, like I know that some kind of load will be applied on a length or an area with little, arrows or an intensity that's distributed over a length or an area, then that will lead me to modeling it as a distributed load. So for this case here, if I imagine the Golden Gate Bridge to be simply supported beam, so I can represent the loads that I have of all these people as just a single load in some way. And this single load, I call it here uniformly distributed load. And it's uniformly here because it has the same intensity over the length of the beam. And its units are load per unit length. So I can represent their load if I'm now representing this bridge as a 2D beam. So their load would be represented as, let's say, pound per linear foot. So for every linear foot, I will have this number of pounds. Of course, this is for matching with the example that I'm showing here, but distributed loads doesn't have to be uniformly distributed loads. There are different shapes that can be the result of the mechanics of loads around you and different type of loads and different type of conditions and the environment you're dealing with, or the structure you're carrying, or the resistance that you have to provide for as a structure. So that's distributed load. It has a unique unit. It's a load per unit length. So for equilibrium purposes, when I analyze the equilibrium of this beam, I will not analyze each one of these arrows. I will replace it with the resultant of this distributed load, and I will place this resultant at the centroid of the shape of the load. So that now kind of in a unique way relate the lesson that we learned about the centroids to equilibrium, because now I have a shape of load. So I need to figure out where is the resultant, how much is the resultant, and where this resultant applies. So if I go back to this simply supported beam with uniformly distributed load, I can represent this distributed load with a single force. And because it's uniformly distributed, from symmetry here, I can know that the resultant is applied in the middle. And the magnitude of this resultant will be equal to the area of this distributed load, which is basically a rectangle. The height of it is, the intensity of the load is 100 pound per foot, and then the length of the beam is 12 feet. So I end up with 1200 pound. Now remember, if you check the units, it makes sense, right? Pound per foot times foot units. Now we end up with pounds. Another example I show you here is a vertical beam or post or a wall, and it's subjected to this horizontal load, but it's now distributed not in a uniform way. It's distributed following a rectangular shape. Where can this happen? It's wind, right? So wind can actually result in that. So close to the ground, the wind velocity is smaller than the wind velocity when you go higher. So velocity of the wind corresponds to the pressure of the wind on the structure. So the intensity of the load here increases while you go up. Of course, we assume it here to be linear. You can do non-linear analysis, but we like linear stuff, right? It simplifies our lives. So now I have a rectangular shape. So the question is, what's the resultant of this rectangular load, distributed load, and where does it apply? So we know from the information about regular shapes, the triangle, the location of the centroid to where I can apply this resultant FR is from the distance 2/3 of the base from the head of the triangle. So 2/3 of 6, it's 4 meters from the head of the triangle, which is the bottom point here. So now I can know the centroid location of this shape and where it is the point where I will apply the resultant. Now the resultant will be the area of this triangle. So it's half the height, 6 meters, times the largest intensity, which is the height of the triangle, 10 Newton per meter. So that will give 30 Newton. One thing that I want to mention here, that for the triangular shape, the intensity of the load grows from 0 Newton per meter all the way to 10 Newton per meter at a height of 6 meters. So unlike the uniformly distributed load, every length of the beam feels, for the top example here, 100 pounds per foot. In the triangle example, every foot of this post feels a little different intensity, but I have this linear relationship that I can just represent all of them with the maximum intensity on the top, and everything else is linearly proportional to it. So yeah, the distributed loads are a must to learn, because a lot of loads come not as point loads. A lot of things are distributed, like our own, we human in buildings, we are modeled as distributed loads. And we have to design these structural buildings. And to design them, I have to analyze them, analyze their equilibrium. So you have to deal with distributed loads by replacing them, and replacing them with what? With the resultants, and put the resultant in the right place at the centroid of the shape of the distributed load. So that's it. Thanks for watching, and we'll see you in other videos. Take care.